We're going to cover these last few chapters here that weren't really tested on. Again, we had a test pretty much our exam through chapter 13, I think. So we're going to pick up with chapter 15. And again, here in chapter 15, it was about solutions. And remember that solutions, as we talked about, is the guys that really get the aqueous symbol. And one sec here. Check something. Okay, so solutions, chapter 15. Again, the guys get the aqueous or symbol. Remember, as we were talking about, that there is a difference between aqueous, which is really a solution, and something that is thank you, which is a pure liquid. And again, the difference is they're both really in the liquid state, as we talked about. But again, something that is a pure liquid is sort of like a pure substance usually. And again, something just like water by itself is considered a pure liquid. Aqueous, which is typically a solution, is actually a mixture, as we talked about. And it is a homogeneous mixture, which just by the definition of a mixture means that there's at least two or more things coming together. So again, if you took water, which is a pure substance, and you added, as we talked about, with something like some solid sodium chloride, and you mix those together based on sort of solubility rules there, the sodium chloride will dissolve in the water, and you will get a sodium chloride solution that is aqueous in this case. Really two parts to a solution that we talked about. A solution is made up of what is known as the solute, which again is the smaller part of the solution, and the solvent, which is the larger part of the solution. And again, in this example, as we talked about, our solvent here would be water. And again, our sodium chloride in this case would be the solute. As we also talked about, typically speaking, if you're not really sure what the solute is for a solution, it is the name of the solution, which is basically the solute. So again, if you have the sodium chloride solution, it definitely is sodium chloride. That's the solute. Remember, as we talked about, and we'll kind of touch upon here again, water a lot of times is a very common solvent that's used, especially for things that are ionic and polar. But remember that water may not always be the proper solvent to use, depending on what your solute is. And as we saw in the experiment yesterday, water doesn't do a very good job of dissolving things that are non-polar, right? So you won't make a solution in that particular case. Now, we talked about the idea of sort of solubility with solutions and just in general. And it brought up that idea that we talked about of like dissolves like. And as we talked about, what that essentially means is it really does sort of fall back to some of that stuff that we talked about in chapter 14, mainly those intermolecular forces. And again, if you remember, there's really kind of three types of intermolecular forces that we talked about. We have dipole interaction, and this is basically the main sort of intermolecular force for polar molecules that cannot hydrogen bond. Speaking of hydrogen bonding, that's another very strong type of intermolecular force. So hydrogen bonding is also the main sort of intermolecular force for a polar molecule that can hydrogen bond. And really, hydrogen bonding is a form of dipole-dipole interaction. Now, remember, as we talked about, just because something has a hydrogen, it does not mean that it can hydrogen bond. So again, you need to have a hydrogen that is directly attached to basically a nitrogen, oxygen, or fluorine. And those three elements, if you look on the periodic table, once again, are the most electronegative elements you could kind of have heading upwards and to the right on the periodic table. What that's going to create is a really good charge separation, a positive negative side to that sort of bond. And that is sort of where the sort of intermolecular forces happen. Remember as well that pretty much all intermolecular forces is pretty much the same type of interaction. They basically, molecule to molecule, the positive side of one will be attracted to the negative side of another. So again, that is what kind of brings those guys together. Um, in addition to some of these, we did talk about sort of ion dipole interaction, and that is basically what happens when you take an ionic thing and kind of dissolve it in a polar molecule. And that is basically what happens when you take like an ionic solid in water. And as we talked about, basically the water molecules, because it's polar, has a positive side, negative side, it's able to surround all the ions. And that's what helps, for example, say like the sodium chloride dissolve in that solution. The last type of kind of main intermolecular force is dispersion forces. And dispersion forces is really the main type for nonpolar molecules. And remember that dispersion forces, really anything could kind of do dispersion forces, but for nonpolar molecules, that's basically its main route of interaction that's going to happen. And out of all three of these things, it is the hydrogen bonding that is the strongest, and it is the dispersion forces that is the weakest of all those forces. Remember that really, in order for a dispersion force to happen, you kind of have something happening to that molecule. Either the electrons are kind of going to one side of the molecule or another, or something is causing that typical nonpolar molecule to basically temporarily gain a charge on one side and the other side of it that it normally does not have. So that's why it is the weakest along the way. Again, these sort of forces from chapter 14 that we talked about are really important here, with the idea of like dissolves like. And basically, things will mix together if whatever is coming together uses basically the same type of intermolecular forces. So if they could use the same type of intermolecular forces, you would expect those things to be soluble. And that's why when we talk about sort of solubility of solutions, typically things that are ionic and polar is going to be all good to go. Again, they're going to be able to do sort of that ion dipole interaction. Things that are polar and polar, once again, are going to be good to go, like we saw yesterday. We had methanol and water mixed perfectly fine, right? So they're going to be good to go. They'll use either hydrogen bonding, or they'll use dipole-dipole interaction to sort of make that work. Also, nonpolar and nonpolar molecules also are going to be okay. They're going to use some type of dispersion forces as their main route. In addition to dispersion forces, as we also talked about, the strength of the dispersion force does increase with molar mass. So more molar mass, more electrons, the stronger the dispersion force, even though it is the weakest. So as we talked about, really you kind of run into trouble when you really kind of cross over and go from sort of polar and non-polar together. They really aren't going to mix. And again, as we saw, with the iodine, which is nonpolar, and water, which is polar, they did not mix. Also, when we took water and I think it was heptane, which is nonpolar, those guys didn't mix and they created different layers. As we talked about in the lab yesterday, we do sometimes talk about solubility and being soluble or insoluble a lot of times, with sort of solids either forming or not forming. And sometimes when we're talking about liquids and mixing two liquids together, those words that we used in the lab yesterday, miscible or immiscible, basically mean the same thing. So if something's miscible, it is soluble. If something's immiscible, it is insoluble. And again, those words are sometimes used for the relationship between two liquids coming together. Also, unlike when we have a solid involved, if something is immiscible or insoluble to liquids, what we end up seeing is layering of the liquids happening, like we also saw yesterday. We saw those kind of different layers to sort of happen. Now, we also talked about types of solutions, and when we talked about types of solutions, there's three types of solutions. There's an unsaturated solution, There's a saturated solution, and there is a super saturated solution. In addition, we also talked about other ways to sort of classify solutions as either a dilute solution or a concentrated solution. So when we talk about an unsaturated solution, that is a solution that will continue to dissolve solute. It has not hit the maximum. So it has not hit the maximum solute that will dissolve. So again, if you have an unsaturated solution, it definitely will continue to dissolve if you put more solid in it. And it will continue to dissolve until you hit the saturation point, which is the point where you hit a saturated solution. Now, a saturated solution is a solution that has the maximum amount of solute that will dissolve at a given temperature. And at this point, if you really are at a saturated solution at a particular temperature and you try to, again, continue to dissolve more solute in it, it will not dissolve, basically just kind of pile up there on the bottom. And then obviously a supersaturated solution, like we saw yesterday as well and talked about, is a solution that has really too much solute dissolved at a temperature. And as we talked about, one of the ways you can make a supersaturated solution, again, is oftentimes you heat up the solution as you're making it. And as we talked about, temperature plays a pretty big role in terms of solids and liquids, or the solubility of solids and liquids. As you increase the temperature, again, you could get a lot more of that solid to dissolve at the higher temperature than you could at a lower temperature. So as you're heating it up, you're going to get a lot more of that solute to dissolve. And typically when you make a supersaturated solution, what you then do is really just leave it undisturbed, let it cool back down to a lower temperature. And when it does so, it cools back down to a lower temperature, two things happen. Obviously, it is still a liquid at this point, but you've actually changed the solubility of that solution because now it's at a lower temperature, which means less solute should be able to be dissolved. But the problem is it's already dissolved at this point. And as we saw, you could just basically do very little things to it that will make all that solid come out of solution, like what we did. Again, we just took like a speck of whatever was dissolved in there and just added it. And that was enough really to cause all that excess solid to come out of solution. And as you saw, I went from a liquid state to a solid state in that case. We also talked about dilute solutions. And dilute solutions are solutions that have a smaller amount of solute dissolved in it. While if something is more concentrated, it then has obviously a larger amount of solute dissolved in it. Any questions on that so far? All right. Then from here, we actually started talking about concentration sort of units and ways to calculate concentrations. So we have some percent concentrations, which is our percent mass to mass. We also had percent volume to volume, and we had percent mass to volume. So these are sort of three sort of percent concentration units that were used. The percent mass to mass is the mass of the solute over the mass of the solution times 100%. The volume to volume is the volume of solute over the volume of solution times 100%. And lastly, our mass to volume is the mass of the solute over the volume of solution times 100%. Remember as well that out of all three of these, this is the one very commonly that people sort of mess up on. And it's really because a lot of times in these sort of questions, you are given the mass of the solution really kind of separated into its two parts. So very commonly, you're given the mass of the solute and the mass of the solvent separate. So you do want to make sure that you actually do get the mass of the actual solution together. Again, as we talked about, it's a very common error that people make, that they just kind of look at the solvent number, which is usually the larger number, and use that on the bottom. But you do want to make sure you actually get the mass of the solution. Obviously, as we also talked about, you could definitely plug and chug into any of these sort of formulas. But you could also, if you are given sort of the percent composition, whichever one, and typically speaking, in terms of units here, this is kind of like grams over grams. A lot of times this is like milliliters over milliliters, and this is like grams per milliliters. Typically the units, they do cancel out and become a percentage at the end when you do the calculation. But if you are given the mass or the percent, for example, again, a 4.25% by mass, calcium chloride solution. One of the ways you could kind of use this to your advantage is to turn it again into a conversion factor, and you could just assume 100, and that would get you two conversion factors, 4.25 grams of KCl and 100 grams of solution, or in 100 grams of solution, there is 4.25 grams of KCl. So you could take a more dimensional analysis approach if you have a problem, and you might not even have to worry about rearranging the equation or remembering the equation. Just kind of take that dimensional analysis, opposites cancel, and use it more like a conversion factor, and it will kind of rearrange the equation for you sort of properly. If you know the grams of solution, you can obviously use it in this fashion here, and that will tell you how much solute that you would need, for example. And that guy's will give me grams of KCl. Obviously, if you knew how much solute, you could figure out how much solution you would have and stuff like that. So it's a very common sort of that you want to kind of maybe use as a conversion factor. In addition, here, talked about probably the most common unit of concentration, which is molarity. And molarity is moles of solute per liter of solution. And it simply is, usually big M is moles per liter. Again, you could think of this as the formula that you use in sulfur. Really, any one of these three things, which very commonly we do, liters in this case, would be moles divided by molarity, and moles would be liters times molarity. Now, one of the things that's really important, and again, where people sort of miss the whole volume part of the concentration unit, especially with molarity, is you do want to, as we talked about a lot of times in sort of calculations, especially if you're given the molarity, you do want to kind of turn it into really more of a conversion factor. And again, if you are given the molarity, you can basically show both of the units, moles per liter. The number always stays with the moles part, and it's always per 1 liter when you do the molarity. You could also, again, use this in the opposite direction. And a lot of times it's a really good approach to take a dimensional analysis approach to these calculations, especially if you're given the molarity. That way you can at least visually see the liters and where it's at, because as I mentioned before, very, very common error. People just kind of look at that and all they think in their head is moles, and they don't even think about the volume part or where the volume part is. The other really important thing when you're using molarity and you're using volume, you do need to make sure that this is in liters, the volume. You do not want to really use milliliters, although you can use milliliters, and it is an okay calculation. It most likely will give you a unit that you're not looking for. So a reminder that when you take liters times molarity, you're basically going to end up with moles when you do this. It's because it's liters times moles per liter, which is the molarity. The liters will cancel. If you decide to take milliliters times molarity, you do not get moles. So you do not get moles out of that. And that's because technically when you do that, you're actually doing this calculation. The molarity is actually millimoles per milliliter. So when you do that, you end up with millimoles and not moles. So if you think you're getting moles at the end of that calculation, you're going to be off by like a factor of 1,000, right? And that's not going to be good as well. So if you're just straight up using molarity and volume, you want to make sure always it's in liters and not milliliters, because again, it is a legit calculation, milliliters times molarity, but you again don't get moles, which is what people typically think. Obviously, a couple of things that we talked about with molarity, the higher the big M number, the more concentrated that solution is. The lower the M number there, the more dilute that solution is. Couple common conversions that are used with molarity that very commonly happens is a lot of times you're given things in grams, you need to convert to moles. So again, that is the molar mass from the periodic table in grams per mole. And I would say probably the milliliters to liters conversion is definitely one that's used a lot with molarity. And again, 1,000 milliliters equals 1 liter. So those are, again, very common sort of conversion factors that are typically used. Now, speaking of sort of solution and concentrations and dilute and concentrated solutions, a lot of times we do a dilution to make a solution less concentrated. And when we do a dilution, the only thing that's added is more solvent. And once again, in a lot of cases, that's water, but not always going to be water as your solvent. And what that means, because we only typically add water or the solvent, the moles of the solute before the dilution and after the dilution will be the same. So the moles of the solute after will equal each other. Again, the only difference here is you are basically adding solvent. Why does the concentration decrease? As we talked about, since it is really moles of solute divided by liters of solution, the solution is the only part that has the solvent in it. So when you increase the solvent, you're increasing the bottom part here, and that's going to make a bigger number on the bottom and overall give you a smaller molarity when you do that. There is a formula that's very commonly used for dilutions, which is M1V1 equals M2V2. I would say most people roll with this one because molarity is the most common unit of concentration. And that's kind of like before here, your dilution. And typically this is after your dilution. And a more generic version of this equation, as we talked about, is C1V1 equals C2V2. And the C's here are concentration. They really could be any concentration you want, as long as they're just sitting units on both sides. Now, when we use this sort of M1V1 equals M2V2, in this equation, it is okay if you want to leave the volume in milliliters. It will work out correctly for you. You could also convert it to liters if you want to, but specifically if you're using this as a dilution equation, yeah, leave it in milliliters. It will work out. That again is because when you solve for something like M1, which is M2V2 divided by V1, if we just put in our units, molarity, milliliters on top and milliliters on the bottom, they cancel and you're left with molarity. So everything works out. Using that, you can just end up with liters as your volume if you're solving for a volume. Also very common with dilutions is the question you're asked is how much, for example, solvent or water you need to add. So typically, if you need to usually know the volume of water that's needed to make the solution, that's usually a V2 minus V1 type of calculation. So the M1 here is your more concentrated solution. V1 is how much of that concentrated solution you're going to use. Like in your experiment yesterday, you started with 0.1 molar HCl, you use 1 milliliter of it. M2 is your more dilute concentration, and V2 is the volume of your more dilute solution you're making, which in the example yesterday was 100 milliliter solution you made when you did the dilution. That would be your V2, and you would solve for M2, which would give you your new concentration. Questions all on dilutions there. So the next thing we talked about this chapter is, let me see here, yeah. We talked about really solution stoichiometry. And remember that solution stoichiometry, much like all other stoichiometries, really work the same way. All stoichiometries are really the same sort of four-ish steps. You want to always make sure, again, you have a balanced equation. You want to, especially if you need to write the equation, as we did in a number of examples, you do want to make sure that you start with the proper formulas and then balance it and all that good stuff. You then want to convert whatever they give you to moles. And I will say in solution stoichiometry, this step, very commonly we use molarity to kind of do that. And I would say in a lot of cases, we are solving for moles, which again is liters times molarity. And definitely in this case, you do want to make sure it's in liters so that you do end up with moles. You could still do our traditional grams to moles as well. It's sometimes used as well, but sometimes we do that. Remember that whenever we're doing any type of stoichiometry problem, we do want to make sure our determine is it a limiting reagent problem or not. And remember to determine if it's a limiting reagent problem, the question you want to ask yourself is basically, can I get moles of each reactant? And from the information given to you, if from the information given to you, you could directly calculate moles of both reactants, then for sure it's a limiting reagent problem, which if it is, obviously you need to solve, it however you want to solve it, figure out if you have enough of one reactant versus the other, figure out how much each one produces in terms of product, whichever way you want to do that. But you do have to do that. Third step is obviously use your limiting reagent if necessary to do the mole to mole relationship. And lastly, we're going to take those moles to some other unit. And I will say very commonly as well in solution stoichiometry, here's where molarity also sort of pops in. Very commonly, you may just be solving for the molarity like you did in those titration problems. Very commonly as well, you may be solving for the volume as well. So again, that's a very common sort of ending. Those two are a normal ending as well. Moles to grams, you could also kind of do that as well. So these are really, very much the same steps that we do in typical stoichiometry problems here, just kind of incorporating sort of molarity along the way. Now, we talked about just basic sort of solution stoichiometry problems. We also talked about, and we did some experiments the other day with titrations. And titrations, typically what we talked about were acid-base titrations. So remember that if you take a strong acid, let's say strong base, you will form two things. You will form water and a salt. And that when we do a titration, again, we do use a burette. And we do something down here where we have some solution. You could have your base up here. You could have your acid on the bottom. You could switch it around too. We also use an indicator to help us understand when we reach the equivalence point. And remember that the equivalence point is the point in an acid-base titration where the moles of the acid will equal the moles of the base. It essentially is your reactants are basically no reactants left over at the equivalence point. That's usually considered the end of the reaction. And that's usually where we want that color change to occur. So we use phenolphthalein, right? So that's where we want that light pinkish color to basically turn to let us know to stop the titration. Now, typically when we do titrations, there's usually two types of solutions. There's an unknown solution, and there's usually a known solution. And that is really how we kind of do titrations because we have a known solution. Typically, what that means is we oftentimes know the molarity and the volume used. That allows us basically to figure out the moles of our known solution. And then we can use stoichiometry to go from our known solution to our unknown solution and figure out how many moles of our unknown solution was used. And then at that point, we really could calculate kind of step number 4 there, either like the molarity of the unknown solution, maybe the volume and all that stuff of what we needed to use. So it's a very common sort of practice. Titration problems are sometimes in word problems, referred to as neutralization problems and that type of stuff. Or they're asked, how much of this do you need to neutralize this acid to base? So if we had something like hydrochloric acid reacting with sodium hydroxide, this again is a strong acid and a strong base. Remember that that is the type of reaction that we talked about in previous chapter. That is a double displacement reaction. And basically we're going to switch partners here. So these guys are going to switch. And also remember that pretty much when you have a strong acid and a strong base, 100% of the time the water comes from the H from the acid and the OH there from the base. And that typically is where we form our water from. And water is, again, one of the 3 reasons why a reaction takes place. So we'll form our water. And our salt, which is really just an ionic compound, is basically what's left over. Those guys will come together and make our sodium chloride, which is our salt in this case, obviously, here. And remember that if you went through your molecular equation and your total ionic equation, and you broke this apart, this would break apart into H plus because it's a strong acid, Cl minus because of the strong acid, sodium will break apart into sodium ion and hydroxide ion. Remember that when you do a total ionic equation, anything that's a solid, liquid, typically a gas, or a weak electrolyte will stay together. So our water will stay together and our sodium chloride will break apart. And our spectator ions here is the sodium and the chloride, which again, if we get rid of it, gives us really the net ionic equation of what's happening here, which is the H plus from the acid. We'll go find that hydroxide from the base, and we will form water, which is ultimately the net ionic equation that you'll get for pretty much any strong acid, strong base combination that you do. It is that formation of water, which again is one of those 3 reasons why a reaction takes place. Any questions on that there? And I believe that that does wrap up chapter 15 of what we talked about. Any questions on 15? All right, then we roll to 16 here. And 16 is acids and bases. And remember that we have our basic definitions here. An acid really is something that has the ability to produce 3 H plus ions in solution. And remember that what we're talking about is, again, those freely floating H plus ions. They're not attached to anything. They're just kind of free in the solution. A base, on the other hand, is something that can produce free hydroxide ions in solution. And again, that's kind of a similar deal. Free OH minus, not really attached to anything, floating around the solution. The main thing that we talked about in terms of acids is in acid-base chemistry, H plus and H3O plus are basically the same thing. H3O plus is the hydronium ion, and H plus is the hydrogen ion. Again, it is sort of used interchangeable both in formulas also. Well, again, a lot of books now will use H3O plus, but again, H plus and H3O plus. It pretty much means the acid part of the solution. And a more general definition that is also very commonly used of acids and bases is the Bronsted-Lowry definition. And the Bronsted-Lowry definition is an acid is a proton donor. And remember that H plus is also sometimes referred to as a proton in acid-base chemistry. And a base is a proton acceptor. And that again is going to be something that gains an H plus in our acid-base sort of chemistry. The result of sort of the Bronsted-Lowry definition is we actually do create sort of partners on the other side of the arrow. So for example, we take a look at two sort of examples. We have our HCl, which is going to dissociate in water. And if you want, you can include the water. And this again is how we do get the H3O plus to be formed. This is going to be our acid, and water in this case will act as our base. And it's the HCl that's going to send the H plus over to the water. That is where we're going to generate our H3O plus. And when it does so, we will sort of lose an H plus and be left with Cl minus. This is what creates our conjugate partners on the right-hand side of the arrow. And our acid on one side is related to what is known again as the conjugate base on the other side. And the base on one side is related to what is known as the conjugate acid on the other side. And once again, in order for any of these guys to be partners or pairs, it is only one H plus difference. So in order for something to be considered a Bronsted-Lowry acid-base pair, that can be the absolute only difference there is one H plus. We also talked about the plus part of that hydrogen being transferred and accepted. Again, when you lose a H plus, you become one more negative, which is why we end up with Cl minus on the right-hand side. When you gain an H plus, you become one more positive. So again, it's the charges also change along the way. Another example here, NH3 that we saw, plus some water here. And in this particular case, the water is going to actually act as the acid, and the NH3 will actually act as the base. The water is going to send the H plus over to the NH3, and that's going to give one more hydrogen to the NH3 and a positive charge because it gained a hydrogen. And the water will lose an H plus and become negatively charged and become hydroxide. Again, our base on this side will be related to our conjugate acid on that side, and our acid will be related to our conjugate base on the other side. And once again, the only difference between the left and the right there are the partners is a 1H plus difference. We also see here, as we also talked about, that there are certain substances can act as an acid or a base, depending on the situation, and that is what is known as being amphoteric, can act as an acid or a base, and water is an example of that as well. Now, again, a reminder that when you're talking about sort of acids and bases, just regular old acids and bases, they are found on the left-hand side of the arrow. All your conjugate partners, conjugate acids, conjugate bases are found on the right-hand side of the arrow. Now, after we talked about that, we talked about sort of the relationship of acid strength, and we did have a list of some strong acids, which, as I mentioned, as you go through your chemistry career here, it's a good list to know. Again, strong acids: hydrochloric acid, nitric acid, perchloric acid, hydrobromic acid, hydriodic acid, and sulfuric acid. These are all strong acids or strong electrolytes, which will 100% break apart into solution. And because of that, they're going to generate a lot of H plus in the solution really quickly, and that's why they're considered strong acids. Anything off of that list would be a weak acid. So there's a couple of weak acids we talked about, and there's a bigger list, obviously, than this. But Things like hydrofluoric acid, acetic acid. These are sort of weak acids along the way, and there's a bunch of other ones. But as I mentioned before, this list is a really good one to know because pretty much if it's not one of those six and it is an acid, it's a pretty safe bet it's going to be a weak acid. So by process elimination, as we talked about, knowing those is really well. In terms of our bases, our strong bases, as I mentioned, is pretty much group 1 and 2 from the periodic table that has hydroxide attached. So things like sodium hydroxide, potassium hydroxide, calcium hydroxide. And once again, if you kind of go group 1, lithium, and then kind of come down, sodium, potassium, make a right-hand turn there at calcium, strontium, and barium. Pretty much any of those guys with hydroxide, again, going to be a pretty safe bet. That's going to be a strong base. Again, a strong base is much like an acid in the sense that it is a strong electrolyte, which means when it goes for a swim, it's going to 100% break apart, and it's going to produce a lot of free OH minus in that solution really quickly, and that's again why it's considered a strong base. Again, probably the most common weak base that you'll come across a lot of times is ammonia, and ammonia is a very common weak base. It does not have hydroxide in the formula. It's got to go find some water and do some reaction to produce hydroxide, but it's able to produce hydroxide, as you can see right here, by reacting with water. And again, that is why it's considered still a base, but it's a much weaker base than something like sodium hydroxide or potassium hydroxide, which is basically carrying the hydroxide with it, and it's able to basically release it. We talked about some relationships in terms of figuring out if a solution is acidic, basic, or neutral. The first major one was Kw, and that is concentration of H plus and OH minus, and that does equal 1 times 10 to the minus 14. Remember, again, you could go with H3O plus here instead. And again, same thing. And the nice thing is, if you know either the H plus concentration or OH minus concentration, you can figure out the other. It is the exact same calculation, regardless of which one you're given. It is 1 times 10 to the minus 14 divided by the other concentration. As we talked about in this chapter, you definitely want to make sure you are using your exponent button, or you may be in some trouble. Yeah, for sure. And we could use the result of this to help us determine if a solution is acidic, basic, or neutral. If the H plus concentration, which is really the acid part, is greater than the OH minus, which is really the base part of the solution, then it's going to be an acidic solution. If the H plus concentration equals the OH minus concentration, then they both will equal 1 times 10 to the minus 7, and they will be a neutral solution. And if the H plus concentration, which is the acid part, is less than the OH minus concentration, which is the base part, then it's going to be a basic solution for sure. So you can kind of use the comparisons there. Also, a reminder, as we talked about, when you're comparing those concentrations, the negative exponent on the concentrations is important. The smaller negative exponent is going to be the larger number when you're comparing them. So sometimes people just kind of look at the number and forget about the negative part of it. With that, we got into a conversation about obviously the pH scale. And the pH scale again runs from 0 to 7 to 14. Below 7 is acidic. Above 7 is basic, and 7 is neutral. As we go from 7 towards 0, you're going to become more acidic. Go from 7 to 14, you're going to become more basic. And we could calculate the pH. The pH is going to be negative log of the H plus concentration. Once again, can also use H3O plus in there if you like instead. And remember that when you punch this into your calculator, depending on the type of calculator, you got a display calculator. Again, you're going to go negative. You're going to go log button, and you're going to go the number, probably using your exponent button. If you have a non-display, you got to go backwards. So you're going to start with the number using your exponent button to punch it in properly. you're going to hit the log button, and then you're going to hit the negative button to do that. Again, a reminder that in terms of sig figs, the number of significant figures in the concentration equals the number of decimal places in the pH. Remember, it is not sig figs to sig figs in this case. It is sig figs to decimal places, and going backwards, also decimal places to significant figures. A similar scale to pH is pOH, which measures the hydroxide concentration minus the log of the hydroxide concentration. Again, it does tell you what you need when you look at it. And the relationship between pH and pOH is an important one, because if you take the pH plus the pOH, it equals 14. So this does give you some options in terms of how you could solve certain problems. If you have the hydroxide concentration, you could calculate the pOH, subtract 14, and get your pH. If you have the hydroxide concentration, you could still use Kw to get the H plus and then go into the pH. So you do have some variety in terms of how you do it. Remember that when you are trying to determine if something's acidic, basic, or neutral, there is just one answer to that. And once again, I would definitely look at the pH when you're trying to determine if something's acidic, basic, or neutral, because that's the scale most people have in their head. You should not be given multiple answers on that question when you're asked that. And again, people sometimes do, as we talked about, people calculate the pH and then the pOH, and they go, cool, one's above 7, so it's like a basic, and one's below 7, it's acidic, the same solution. So just look at the pH, that's usually what they have. The pOH scale does run opposite of the pH scale, so you want to keep that in mind. We also talked that if you do have the pH directly from that value, you could get the H plus concentration. And again, that's going to be the inverse log of the negative pH. And on most people's calculators, when they punch those buttons, it sort of looks like this. A 10 and a caret's usually popped up. Once again, to punch this one in, if you have a display calculator, you're going to go with your second button or shift button up on the top left corner usually, and you can go with the log button that has like the 10 to the x, and then you're going to do your negative button and then obviously your number. If you have a non-display calculator, you got to start with the number. You need to make it negative. You then need to hit your second or shift button and then your log button, and again, that will get you hopefully the right answer. In addition, if you have the pOH, once again, you can get directly from that the hydroxide concentration, and that's going to be the inverse log of the negative pOH as well. So you do have a variety of ways to solve some of these problems depending on sort of which path you take. They all should really get you to the same answer. Maybe slightly different if you did a little bit more rounding than not, but they should get you there. Any questions on the different ways to calculate things? We talked about towards the end there as well what to do if we have a strong acid or strong base, if we want the pH of a strong acid or a strong base. And really, because they are both strong acid or a strong base, they are both going to be a strong electrolyte. And because of that, if you had something like hydrochloric acid, it will 100% break apart into H plus and Cl minus, much like what you did in the lab yesterday. And this is going to be 100% of what you got going on. So if you know the molarity of this guy, you can figure out the molarity of the H plus. And because most strong acids are monoprotic, they only have one hydrogen, pretty much the concentration of the strong acid will be the concentration of the H plus, and that would allow you to go directly into your pH equation at that point, and you can figure it out. If you have a strong base, on the other hand, it does not have H plus in it, but it has hydroxide, and it will break apart into sodium and hydroxide. And remember that as well, that the H plus concentration and the hydroxide concentration are related to each other. So as one goes up, the other goes down, and vice versa. So in this case, we're not really interested in the H plus in a sense, but we are interested in the hydroxide, and that's going to help us get to our pH. And once again, it is going to have 100% of these ions, and it is a 1-to-1 relationship in this particular case. So the molarity of my sodium hydroxide would be the molarity of my hydroxide. It is important to remember, and a very common mistake that people make is they just get that number and automatically think, cool, let's go right into the pH. But again, that is the hydroxide concentration, which means you need to first go into the POH with the hydroxide concentration. So you got to go into here first. And once you get that, then you could go to the pH would equal 14 minus the POH. So again, you have an extra step, if you will, with strong bases because you get the hydroxide concentration. You got to go POH first and then to the pH. Now, any questions on that? As we also mentioned the other day, probably out of the two, in our case, a strong acid or a strong base, the strong base might be the only one where you might have to adjust the concentration, especially if it's a strong base from group 2 on the periodic table. That most likely will give you 2 hydroxides. So you do want to make sure you're using the correct hydroxide concentration when you do that. The last thing we talked about in this chapter was buffers. And by the way, as we also mentioned for our class here, we only deal with strong acids or strong bases. We don't deal with pH of weak acids or weak bases. You'll deal with that in 1B. If you take 1B, that's where you'll deal with that. For buffers, which you also will not see again probably until 1B, are basically solutions that can resist changes in the pH even when you add acid or base to it. And really, we'll call it big changes to the pH. So there are solutions that can resist really big changes to pH if you add acid or base to it. The reason for that is what they are made of. So they are made of a combination of either a weak acid and the salt of its conjugate base, or it is made up of a weak base and the salt of its conjugate acid. And that's really what makes a buffer sort of a buffer. Because it deals with a weak acid or a weak base, they are weak electrolytes. And what that's able to do is actually keep in solution both the acid part of the buffer and the base part of the buffer. So you actually can keep in that solution both of those things. So your buffer you can think of as having like an acid part and a base part, and they're able to do that. Something that's a strong acid or strong base, because they will completely break apart, cannot keep both parts of that in solution. You will end up with either like just a base or maybe just an acid. You won't have an acid part or a base part with a strong acid or strong base. And that's why you cannot have a buffer that's made up of a strong acid or strong base, because it will not act as a buffer. Now, we talked about really how it works, and just quickly reminder of how a buffer sort of works is if you add something to water which is not a buffer, like our hydrochloric acid. So if you added that again to water, it's going to completely break apart into H plus and Cl minus. And because of that, you're going to have 100% of those guys. And again, if you toss that HCl into that water, which is not a buffer, what we are going to do, as you can see, obviously, and we talked about, is it's just going to produce a lot of free H plus. And because of that, what we're going to see is the concentration of H plus skyrocket, and we're going to see a pretty big drop in the pH. It's going to drop really a lot, because what you just did is introduce a bunch of free H plus into that solution that now has a lot more H plus than it does hydroxide, and we're going to see a really drop in it. Now, if you took something like a buffer, like we talked about, like say an HF, sodium fluoride, this is a buffer. That is a weak acid and its conjugate base, the salt of its conjugate base. As we talked about, it's really here the F minus and the HF that are the buffer part of it. The sodium is just a spectator ion that's hanging out, not doing much. But the difference is when you have that solution, unlike, say, water, you will be able to have the HF in that solution. You'll have some H plus and you'll have F minus. So as we talked about, you will end up here in the buffer solution with an acid part and you will have a base part. So now when you take the same HCl and you toss it in there, it is actually going to go through a little reaction. The HCl, which is an acid, will react with the sodium fluoride in this example, which is the base, and it will do a double displacement reaction, and it will form some sodium chloride, and it will form some HF. And one of the things that very much happens in a buffer is when you add acid or base to a buffer, you actually will use up part of the buffer, but you'll make the other part of the buffer. So it's sort of regenerating a little bit in that sense. And because you made the part of the buffer that was there originally, it's not going to affect the pH. Sodium chloride is a neutral salt. It won't affect the pH. And the key here is what we don't have is we do not have free H plus formed. And because of that, the H plus that we started with in this solution will remain relatively constant. And because of that, the pH will not shoot around all that much. It will stay pretty much where it's at. Will it go down a little bit in this case? It will, but it won't make a giant jump like we talked about from like a pH of 5 down to like a pH of 1. There won't be this big drop in it. It'll go from maybe like a 5 to like a 4.9 or something like that, maybe 4.95. It won't drop a lot. So the way a buffer works is because it does have an acid part and a base part in it. When you make a buffer, you have your acid part and your base part. It is well equipped to, when you add additional acid, that it will then go and react with the base part, but will actually make some of the acid part. So it will increase the acid part of the buffer and it will use up some of the base part of the buffer. But the key is when you do that, all that H plus that wants to come in is prevented from being freely in the solution. It ties it up basically. So it ties that H plus up with the base part and it's not freely floating in that solution. So when you add a base to it, which is basically going to add hydroxide, it's going to react with the acid part, but make some more of the base part of the buffer. And it also is going to tie up with the acid part. And that hydroxide, which normally would be freely floating, is now going to go hook up with the H plus and make water. And it's no longer free to increase the hydroxide concentration. So a buffer, because it has both of those components, an acid part and a base part, prevents the formation of free H plus or OH minus in the solution. And both of those things basically allow the pH to remain relatively constant. You don't get these really big shifts in the pH that you would if you did not have those things in the solution like you have in water. Any questions on that there? All right, then the last chapter we talked about for the season here was 17. And we talked about reaction rates. And remember that there are ways to sort of increase a reaction, things like concentration. So if you have more or higher, typically will increase the rate. If you have obviously lower concentration, it will decrease the rate. Temperature is another really big factor. If you increase the temperature, typically the rate will increase. And if you decrease the temperature, typically the rate will drop. And the reason for that is some of that stuff we talked about in chapter 10, those sort of energy diagrams, where we have reactants and products, and we have that activation energy hill. Remember that when reactants are moving towards the product side, they have to break all their bonds and start making new bonds. And when they get to the top here, that hill that they have to climb is the activation energy. So by increasing the temperature, there's going to be more reactant molecules that have enough energy to get to the other side. And decreasing it will do obviously the opposite effect. Remember at the transition state here, we get a complex that kind of quickly drops down to the other side. This is an exothermic diagram, right? Because energy is being released as our reactants are higher in energy than our products. Obviously, an endothermic will look a little different. It'll look like this, reactants to products here. And again, we would have our activation energy hill that things have to climb. Remember that another way that we could speed up a reaction is we could add a catalyst, right? And a catalyst, again, is not a reactant, not a product. It does not get used up in the reaction. It's there really to facilitate the reaction occurring in a more efficient way. And that usually will result in, if you look at an energy diagram, because it's occurring in a more efficient way and does not get used up, it will lower that activation energy hill. So if this blue is sort of the catalyzed one, is a less of an energy barrier now for reactants to get to the other side. So there's going to be more reactants that's going to be able to get to the other side a lot easier. And that's going to result in a faster rate or reaction occurring in most cases. The other thing that we talked about was equilibrium, which again, you won't really see until 1B. But equilibrium deals with, as we talked about, a certain type of reaction, which are these reversible reactions. And those are the reactions that basically have arrows heading in both directions. So as we talked about, heading from reactants to products is sometimes referred to as the forward direction. Going from our products back to reactants is the reverse direction. And that's what happens in these type of reactions. You start to make products. At some point, those products will recombine and go back the other way. And we can basically write an equilibrium expression here, which is capital K. And that is the concentration of C to the C, D to the D. We take it to the coefficients here. And products over reactants. These do need to be equilibrium concentrations to go into here. The K value is just a number, no units. But it does tell us several things. It tells us that if we have a large value of K, that means that when we reach equilibrium, we mainly have products. And if we have a small value of K, that means that when we reach equilibrium, we mainly have reactants. And remember that when we do say we've reached equilibrium, it does not mean that we have equal amounts of everything on both sides. When we talk about reaching equilibrium, what it means is the rate of that forward direction will equal the rate of the reverse direction. And as we talked about, what that essentially means is everybody will get locked into place, their concentrations at that point. So once they reach equilibrium, they will be able to maintain their concentrations or their pressures unless you do something to kind of screw it up. And speaking of screwing it up, that's what we finished talking about in this chapter, which was Le Chatelier's principle. And the idea of Le Chatelier's principle is we have really a system at equilibrium, and then you add a stress to it. And when you add a stress to it, it will mess up the equilibrium. And as we talked about with these type of reactions, is that they want to get themselves back to an equilibrium state. So they're almost self-correct themselves to do so. And it will get back to an equilibrium state by basically doing one of two things, either shifting to the right, shifting to the left, are no change. And again, shifting to the right means you would make more products. Shifting to the left in terms of the equation, you would make more reactants. So we talked about several stresses here. We talked about concentration. And really, there's two things you could do for concentrations. You could add more, and if you add more, it will shift away from the side you added. If you remove, it will shift towards the side you removed it from. And when we talk about sides, we are talking about the equation basically. So if you add more reactants, it will shift to the right and make more products. If you add more products, it will shift to the left and make more reactants. Really, what's happening here, as we talked about, is either you're going to cause the forward reaction to occur or you're going to cause the reverse reaction to occur. So when you add more reactants, so if you added more of this, you have now more reactants and products going to shift away and cause the forward direction to occur. If you remove something, so if you remove that guy, again, it's like you created a hole on that side. But really, what you have now is still more reactants and products, and it's going to shift towards it when you remove it. So always kind of goes towards it. So as I mentioned, AA is a good way to remember that. Add away. And wherever you remove it, you can think of it like a hole. You need to kind of fill the hole. So it'll go towards the hole and kind of fill it in that case. Other sort of stresses that we talked about dealt with pressure and volume. And these usually are related to gas sort of equilibriums. And it does relate to sort of Boyle's law. If we increase the pressure, we will have typically a smaller volume. And really, the change that occurs is the pressure starts to go up. So we want to bring the pressure back down. So, in a smaller volume, to bring the pressure back down, we need less gas molecules. So it will go to whichever side has the least number of gas molecules. That obviously is reaction dependent as to which way it has it. You just got to look at everybody with a G and add up the coefficients on each side, and that will tell you. If you, bless you, if you decrease the pressure, the volume increases. So the change that occurs here is the pressure starting to drop. We want to bring the pressure back up. So in that larger volume, we're going to need more gas molecules. And by having more gas molecules, that will bring the pressure sort of back up from the change that occurred in there. Also, again, dependent on the equation you're looking at as to which side would have more or least. Temperature is another sort of stress that we talked about. It does work the same as concentration, and we can increase the temperature and it will shift away. And we can decrease the temperature and it will shift towards it. Now, what determines sort of which way that is you also need to figure out what type of reaction you're dealing with. Is the reaction exothermic or endothermic? So remember that if it's exothermic, energy is going to be released, and that usually means delta H is going to be a negative number, which is our change in enthalpy. And if it's endothermic, energy is going to be absorbed, which usually means the delta H is going to be positive. But what does that mean in terms of the reaction? Well, if you have a exothermic reaction, heat and energy would be considered a product in an exothermic reaction. If you have an endothermic reaction, heat and energy would be considered a reactant. And again, so if you have an endothermic reaction and you increase the temperature, it will shift away from the reactant side and go to the product side. If you have an endothermic reaction, you decrease the temperature, it will go towards the reactant side. So those are, again, very common ways so you can kind of figure that out. The last thing we talked about in terms of Le Chatelier's principle was a catalyst. And again, as we talked about, it's not a reactant. It is not a product. And it does not get used up. Again, it's there usually to speed up a chemical reaction. And in terms of Le Chatelier's principle, it is one of the things that will basically cause a no change sort of situation to occur. Other no change situations, as we also talked about, is you could have equal numbers of gas molecules on each side. And in the case of pressure and volume, that also would cause a no change. And lastly, as we also talked about, is a noble gas, sometimes added, will cause a no change. So those are three sort of common ways that would cause a no change situation. And I believe that is all we talked about in chapter 17. Any questions on those there?